All right, so let's talk about writing functions. This is going to be one of the longer lessons throughout this course. However, really we're just kind of touching the very surface of writing functions. And this can get into a lot of deep, more complex type of concepts, but we're going to keep it pretty simple. But the reason I kind of lead off with that is because I really like Hadley Wickham's comment that is on this slide here. Writing good functions is a lifetime journey. So what you're going to learn today is it's going to give you the basics to go ahead and start writing functions, but really writing functions well and also writing them in a idiomatic way within R. It's a long process to learn this and to get really good at it. I'll provide some resources at the end that can get you going deeper into this area, but at least this part of this lesson, right? The slides that we're going to hit on now that are just touching the surface of writing functions will get you enough information to kind of get you going in the right direction. All right, so what are we going to hit on? Well, we want to talk about why functions are good. We're going to hit on the anatomy, the primary parts of a function. We're going to talk about how we define functions and also define the arguments that we'll be using within our functions. And then we'll look at different ways that we can, as we're developing functions, that we can kind of validate that certain arguments or other conditions hold and how we can communicate to the user if they do or do not hold. And then at the end, we'll talk about different ways we can distribute our functions. All right, so why are functions good? Well, functions provide a centralized abstract method for a single operation or functionality that we're trying to apply within R, and that it's something that we use over and over again, right? And so writing good functions are really focused on how do we increase the reusability of certain code. And this in turn reduces the verbosity and the repetitiveness within our code. Also reduces the chance of making errors. Along with when we need to make updates in our code, we have one central location that we can update code versus trying to find all the different areas across our source code that we implemented some task. For example, this is basically some code that comes from the R for Data Science book, and you'll see it in the reading lesson. And you can see that we have a repetitive nature. We're doing some kind of functionality here where we have this data frame, and for each of the columns within a data frame, we're trying to execute some code, right? Basically some code that is doing some kind of a standardization type of a process. Now, within here, you can see that for each column, we have basically the same code, except there's some different input requirements, right? It's very specific for each column. And so lots of times what happens is rather than rewriting this code for each column specifically, we'll write this first line and then we'll copy this and then paste it down here for the second line, for the third or second column, and then do it again for the third column and the fourth. And in doing this, we're bound to make some errors. We're bound to have some mistakes within our code, right? And for example, within these, 4 different lines here, you can see that for this function or this operation that we are defining for the B column, right? When we copy and paste it from A, right, we changed some of the values from A to B, but we missed one, right? And this is an interval. When we start copying and pasting code like this is basically almost guaranteed to happen to us. And writing functions to implement can drastically reduce this type of these type of problems. All right, so to follow along in this slide or across these slides, basically we're just going to be using base R. We've used a lot of packages lately, a lot of functionality that not just built in R, but is also provided by third-party packages and libraries. In this case, we're primarily just using base R. We'll probably see some functions coming from the Tidyverse packages, but that's mainly for examples or basically to apply our functions that we're going to create two data frames. But for the most part, to write a function, we don't need any other packages to do that. All right, so let's talk about the key ingredients of a function. There's four main things to think about with a function. First one is a name, right? And we often want to make sure our names are quite explicit, and that when you see the name of a function, you have a pretty good idea of what it's doing. You can think of a lot of the functions we've seen today from like dplyr, where we have group by, we have arrange, we have summarize, right? These are all function names that give us a pretty good indication as to what we're trying to do, right? So the first thing we're going to do, we're going to name our function. Now, within a function, we are going to have certain arguments of interest, right? So we can see here, we define this function called myFun, and we do that by assigning, right, this body function here to this variable. So this follows the same assignment process when we were creating data frames or other objects. We're creating a function object, right? And we do that by applying this function, and we supply the different arguments that we want to have. Now, arg1, arg2, these are just arbitrary names. It could be anything. You could have x, you could have verbose, you could have whatever different kind of arguments. And we'll get into that a little bit later. And then we use our curly brackets, and that's going to enclose the body of our function. So the body of the function is where all the code that's going to operate on the inputs and provide some output, that is where that is happening. Now the last thing is environment, right? And the environment is all where this function is operating. For most of the functions we're going to create here, we're just going to create them in our global environment. So they're going to be within our local global environment. But functions can have other environments, and you mainly see this when we are calling functions from packages, right? So then they have what we call a namespace environment, where that environment is the package. All right, so we can identify all these different components within our function by using args, body, and environment functions, right? So say we have some given function here, and this is just computing the present value based off of some inputs, and you can see that within my function I've got three different variables or arguments. We have fv for future value, we have r for the interest rate, and n for the number of time periods that we're looking across. And so then we have our body of our function, which is right here, which is going to perform the operation of interest. Okay, so if we wanted to find the arguments of PV, we could just apply args PV, and we see basically we get this interesting output. We don't need to really worry about this null and stuff, but you can see it's going to supply us the arguments from our function. The body PV will supply us the actual code that's going on inside of my PV function. And the environment just says, hey, look, this is a local function that was created and is enclosed within our global environment, right? So if we look at our studio here on the right, if we create this function here, let me go ahead and run this code. We will see now we have our PV function in the global environment. So that's all that this means here. This just means, hey, look, this is a function that you created and that is within your own global environment. All right, so what I want you to do is we've got three different functions here. We have read.csv. Now this is a built-in function within R that can read in CSV files. We have the tidyr contains. This is a function provided by the tidyr package. And we have the sum function, which is built in to R as well. I want you to go ahead and identify the arguments, the body, and the environment of each of these. All right, so let's run through these. If we were to run the args function on read.csv, right, we can see that it's going to list all the different arguments, right? We have the file, header equals true, the separator equals comma, quote, and so on. So these are all the arguments that we can adjust or supply within the read.csv function. Within the body, this is kind of interesting. Within the body, we see that read.csv is simply calling read.table. So read.table is actually another base R function that is a very generalized function for reading in delimited files. Delimited files being CSV files, comma separated files, tab separated, and so on. Right, so read.csv just calls a certain version of read.table that is designed to work on comma separated value files. If we look at the environment, read.csv, it says namespace utils, right? And the reason is because within R, we have the utils package, or that's units, utils package. So this is a built-in package that comes with R. And in here, there's a bunch of utility functions for us to work with. And one of them being read.csv, right? So here we can see when we are actually calling read.csv, it's going to operate in the namespace of the utils, right? So this is telling us where is this function being pulled and used from. All right, if we look at the tidyr contains, we see similar outputs. We get our arguments here. We can see the code within this function that gets ran when we call it. And we see that the namespace is actually coming from tidyselect. Now tidyselect, this is interesting because we called this from tidyr contains. Well, actually, this is a function coming from a tidyselect package, which we typically don't operate directly with, but it's kind of a utility package used by tidyr. And then if we look at sum, we get some slightly different results, right? So we see our arguments, which not a whole lot of, but then for the body and the environment, we get null. And the reason is because sum is what we call a primitive function. And a primitive function is a function that is actually built and written directly in this case, C++. And then what R is doing is it is actually abstracting. It's kind of like an abstraction layer above that, but it is calling the C function of sum. So that's why we get these nulls. All right, so let's talk about defining a function. We kind of hit on this, but let's discuss a little bit more. So the way that we define a function is very similar to how we define or assign some other object. Right? We have the name that we want to use for our object, and then we use the assignment operator, and then we use the function, this function call. Now, one thing is when we're naming a function, it's very helpful to have informative names, like I mentioned before. But lots of times what we want to do is we want to use verbs because functions most of the time are doing some action, right? And so by using kind of a verb syntax or naming structure for our function names, it kind of helps to explicitly state what it is doing, right? So for example, we could have well, earlier we had the PV function. Well, that's not a very informative name. So we may want to actually write that out to be present value, right? Or we may want to have it say compute PV, right? Or estimate PV or estimate present value. So we always are trying to strive for this balance between a good, explicit, informative name, but also not a name that becomes so long, right? So and it's all kind of a balancing trick to figure out what meets that those requirements. All right, so we can actually define a function with no arguments, right? Where basically when you call the function, you make no adjustments. You don't provide it any inputs for it to use. It just does some calculation, the same thing every time, right? So I could have compute PV function. You see I have no arguments within my function call here. And then it's just going to compute this this function that's quite static, right? It's only going to compute the exact same thing every time. And this will work, right? You can see we apply it here, compute PV, and we get our present value. Now, this is rarely all that helpful, right? So we want a function that does one thing consistently, but we want to allow it to have some flexibility on the inputs that it is operating on. So we do that by allowing the user to provide key inputs or adjust key inputs within our function, right? So for example, in what we were doing here, right, we're really taking the future value, some future value, and we're going to use an interest rate and a number of periods to compute our present value, right? So these could be the main things that we want users to be able to adjust. So we can supply those as arguments, right? F, V, R, and N. So now, whenever we have the internal code operating on what will be supplied for these values, right, we just use those as argument names. Okay. So now, when I allow for this functionality, a user can now call, compute PV, and they can assign different values to the future value, the interest rate, and the number of periods, and the actual present value calculated will be returned. One thing to kind of call out here is we actually don't need to use any kind of a return statement. Now, R does have a return statement that you can, but basically, if you don't call a return function, then whatever the last calculation performed will be returned. All right, so what I want you to do, I want you to create your first function here. So define a function titled ratio. So this is the name of the function that takes two arguments, an x and a y, and it returns their ratio, so x divided by y. And then call ratio with arguments 3 and 4, so that x equals 3 and y equals 4. All right, so you should look or end up looking or having something similar to this where we have our ratio, which is a function. Arguments are x and y, right? And you could just have the body be this simple. And then now when you compute ratio of 3 and 4, we see we get 0.75. All right, so when we are calling arguments or we're calling a function and supplying arguments, we can actually do this in a few different ways. One is we can be quite explicit and we can use the argument names. So we can say compute PV, where the FV argument or future value equals 1000, the R value or the R argument equals 0.05, and the N argument equals 10. Now, another way we can do this is actually what's called positional matching. So if we do not supply the argument names, but we do supply values for each argument in the order that the arguments are within the function, it will take it and it will do that computation. Okay, so just realize that we can actually pass arguments without calling the argument name or what we actually call the parameter name. We can do that. We just need to make sure we're putting it in the right order, the same order as expected by the function. Now, if we want to change the order, right? Let's say we want to call the compute PV, but we want to supply the interest rate first, and then the future value, and then N. We can do that, but the important thing here is we have to do it by calling the arguments. We cannot do positional matching. If we try to do positional matching, but we just change the order that we supply them, right, where we supply interest rate first and then future value and then N, the function has no idea what the values are that you are supplying. It is just going to interpret it as you meant to pass 0.05 for the future value, 1000 for the interest rate, and 10 for N, and it's going to compute, which is computing what you likely did not expect, right? So realize you can do positional matching only if you supply the arguments in the order as expected by the function. If you want to change that order, you have to use the name, basically assign the argument name to the value. Now, another thing is if you do not supply all the arguments required, then you're going to get an error, right? So we can see here we pass the future value, the interest rate, but not the value for the number of periods, and we get an error, right? So it says error in this function, argument n is missing with no defaults. Okay, so ordering arguments in your function is important, right? So the way that most people think about functions is you got kind of a order of arguments, and it's based off of kind of the importance that argument has within the function. Okay, and another thing is when we build functions, we should also be thinking about should this function be built in a way that is that operates with the pipe operator. So recall that the tidyverse functions, the tidyverse packages, consistently have data as the first argument. So let's recall that if I do, let's look at dplyr, and I do summarize, and let's go ahead and look, see the first argument is this dot data, right? And if we look at mutate, the first argument is dot data. And if we look at filter, the first argument is dot data. And this is because this is what allows the pipe operator to work, or to work easily and consistently. Because we're piping the output, which is usually the data or data frame, from one function into the other. So if you're building a function that wants to accept a data frame and do some computation on it, then by following this same approach where the first argument is data, then it will be a natural fit to work with the pipe operator. Now, when we think about the ordering of our arguments, especially with positional matching, we need to be thinking about which arguments are most versus least, have the most versus the least amount of importance, okay? And this is because usually functions have a lot of arguments. But sometimes many of the arguments just are not that important, and there's typically good defaults that we can incorporate, okay? So kind of way to think about it is, here's compute PV, and I added, so we've got our future value, our n, our interest rate, and then this digits. And this digits would be for the purpose of rounding the output. Now that's usually not as big of a concern as like, well, the future value that my present value is based off, or the interest rate. Right, so it wouldn't make sense to have digits be up front, whereas in this function call, I have the more important arguments up front and then digits, which is of lesser importance at the end. Now, like I said, lots of times there's arguments that are less important, and typically there's decent defaults that are sufficient. And so rather than making the user call all the arguments, lots of times what we do is we have the first, could be 2 or 3 arguments, the ones that are most important that the user needs to supply. But then for those that are lesser important, then we can create defaults, right? And we create defaults by simply calling digits and then equals whatever that default value is. So here, the default is to set digits to 2, right? So we can see we round the output of our future value, and the round function has a digits argument, and we just simply pass it the digits that the user supplies within the function call. So now when I do this, if I don't even call digits, that's fine. I just pass it the future value, the interest rate, and the number of periods, and it will compute, right? And the default will be rounded to 2 digits. But if the user wanted to adjust it, right, they could either pass it, and here we just do positional matching, or here we do positional matching for the first 3, and then they name or use name matching to assign digits to be 0. All right, so what I want you to do is let's take a look at the code that we saw earlier on. We had the sequence of code that we applied to a data frame to each column. What I want you to do is convert this into a function that's called rescale. And rescale should take basically argument x, so a single argument of x, which is a vector, and executes this code. So think about where we have code in here that is specific to a data frame. and a vector or a column within that data frame. And let's abstract that out and convert that into the variable or argument x that will be called or used within the function. And I want you to go ahead and test it on this vector here, this test vector, to see if it works. All right, so your function should look like this. We have rescale is the name of the function. Function takes one argument, x, which is a vector, and then we pretty much do similar computation. Now, you could have written this a little bit differently. You could have been more explicit to have x minus the min of x divided by the max of x minus the min of x. That's fine. In this case, I take a little bit of a different approach. If you compute the range, so let me show you what the range does here. So I've got my test vector, which is just a vector of values. And if I do range test vector, what it actually does is it passes our min and our max, right? So I'm getting these requirements, this min and the max, directly from range, right? So I compute the range, and then I go ahead and I say x minus the range. 1, that would be the minimum, divided by the maximum minus the minimum. All right, so now I want you to do part 2. Now add an argument to rescale that allows you to round the output to a specified decimal. And I want you to set that argument to have a default of 2. Okay, so now this is how this could look. So the first thing we do is we have a function that allows us to pass x. Digits is going to allow us to round the results, but I'm going to go ahead and set the default to 2. Here was the code that I had in the last part, the part 1 of your turn, and I just saved whatever was computed here to a vector called scaled, and now I pass scaled to round with the digits argument, and it's going to round the output. So now if we just apply rescale, the default will be basically have 2 decimals supplied, but I can go ahead and adjust it to be 3 digits, and then now I get this as the output. All right, so we understand kind of how to incorporate arguments and how to call arguments in different ways and to set defaults. But one thing we often do is we want to be able to check the arguments that a user passes, or maybe there's some other conditions we want to check on, and we want to be able to communicate back to the user certain things. Could be warnings, it could be just a general message, it could be that they supplied some information that was incorrect or didn't meet certain requirements, and we can provide an informative error back to the user. All right, so how can we do this? Well, there's basically 3 different ways, actually 4 different ways we can communicate. One is a hard stop, and so this is to signal an error exists. So basically what we're going to do here is if some condition is met or is not met, then we are going to stop the functionality. Right? And there's 2 different ways we can do that. There's a basic stop function and there's a stop if not. And we'll take a look at those here in a little bit. And that's going to actually throw an error and stop execution of the function at that point. Warnings. So warnings are a way that allow us to signal that something has gone wrong within the function. However, the function can still recover or partially recover and perform some operation. Okay, so it may be that only parts of some conditions were met, but we at least have the most important information to execute basic functionality of that function. And so we can continue operating, but we want to provide some information back to the user that, hey, look, something went wrong, and you may want to look into correcting this. And we can actually provide messages. So a message is simply some kind of informative message back to the user just about, it could be almost anything. Now, an important thing is messages can get a little bit verbose, or they could kind of clog up the RStudio interface because you're getting all these informative messages back. We like to be able to turn those off, and we'll show how we can do that as well. All right, so let's look at stop. So this is throwing an error. So a common initial use of the stop function is to check on arguments, right? So say that we've built our compute function, compute PV, and we've got our future value, our interest rate, number of digits, number of time periods to compute the present value over, and then the digits to round to, right? And we may want to go ahead and make sure that the user is passing the correct type of values for these interest rates, right? So future value, it needs to be a numeric value, right? So if it is not numeric, right, then we could go ahead and throw the stop. And this, we could pass this string here that basically is a informative message to the user, right? In this case, we just say FV, the argument FV must be numeric. And we could do the same thing for the interest rate. And we could do the same thing for N. And we could do the same thing for digits. So you can see here, we got 4 arguments, and we've got 4 if statements that we are checking the values passed by the user. And if any of those are not met, then we're going to go ahead and stop the function call because we can't compute based off of incorrect data types provided. So here we can see if we were to pass in compute PV, here we pass a character string for a future value, and we get this error, FV must be numeric, right? So that would hopefully be informative enough to the user that they need to change their input for the future value to be numeric. Now, this is a lot. I mean, here we've added however many lines of code just to check on 4 different arguments, right? Now, there is a more simple way to do that. The stop if not is a very concise way to say stop if not all these different conditions are met. Okay, so the first condition is future value is numeric, interest rate is numeric, number of time periods is numeric, and digits is numeric, right? It's going to check to see if any of those conditions don't hold, and it'll throw an error, right? So now we do the same thing where we try to compute present value with a character string for the future value, and we get this error in compute PV, and it says is numeric future value is not true. So the thing is, the message that is provided by stop if not, it's in this case it is informative, but there's less flexibility in the type of messaging that you can provide as if you just use stop. However, the benefit is it's a lot more concise. Rather than having to write 4, we could actually go ahead and we could just have 1 stop if not. So that's how to throw some, an error if some condition is not met. Lots of times we also want to throw warnings. And we've seen many of these examples throughout this class. For example, the lubridate package, right? If we pass it here, we have, if you recall, what we're trying to do with lubridate here is to take a character string of a date and convert it into a month, day, year object type. So we can do that on this first one because the information is provided. But here you can see the second element, we are just given the year. We're not given the month or the day, right? So we can't actually compute that month, day, year date type. So we can throw a warning. And what happens now is it will compute and create the month, day, year, date object for this element. But you can see it says warning, 1 failed to parse, right? And the result is an NA, right? So that's an example of where a warning, it's going to be thrown, but we can still execute the code on other parts of the supplied information. So another very common use of warning is when we want to deprecate some either an argument or a function. So say that we had created this present value function at work, right? But down the road, we had to make some major changes, and so we kind of created a new function, compute PV, that does some similar functionality, but it has, maybe more advanced capabilities, right? So at some point, we want to signal to the users, hey, look, we no longer want to use present value. We want to go ahead and use compute PV. So we could have a deprecation warning. So this is just throw a warning here that says present value is deprecated. Use compute PV from here on out, right? And so you can see that that warning is thrown right away. So there's no condition looking to be met here. This is just a warning that will get thrown every time the present value is called, trying to get people to move to a new function. Messaging is designed to be just purely informational. The code still operated, the function still executed, but we may want to communicate something to the user, right? So for example, we've seen this with ggplot. When we use geom histogram, there's just a default number of bins, right? And it's set at 30, but ggplot communicates with you. It tells you a message that we're using 30 bins and pick a better value with bin width. Okay, so that's a version of using messaging to relay some information to the user. Sometimes there could be information about how things were interpreted by the function. For example, when we do read underscore CSV for a certain function, it is going to tell us the delimiter that it is using and how the different types of columns were read in. So here it says, well, we read in a character, a double, and a date time stamp. Or actually, no. Here, what it's saying is there's 4, because we got 10 columns total. 4 of those columns were read in as characters. 5 of them were read in as double floating points, and 1 of them was a date timestamp. Okay, so that's providing information back. And if that way the user could look at this and say, well, I intended to have one of these columns actually be a character string or something else. We could change that. And then sometimes there's just words of encouragement, right? So here is a package that I use internally that help me do a lot of interactions with Git and GitHub, and you can just get some random words of encouragement back saying well done. If you ever do testing within R and using test that, which is a package, they do a lot of that. All right, so to add any kind of a message, right, we can just use the message function and it will return whatever message you supply. So, right, if we just did message here, then it just provides that message in return, right? So in this case, in our compute present value function, what we want to do is if the user passes an interest rate that is less than 0.01 or greater than 0.25, well, this may be out of the norm for that industry or the common business practice. So we may just want to have a message that says, hey, look, yeah, we went ahead, we computed it, but your interest rate seems a little bit out of the normal range. So just want to call that out. And if you need to change that, that's great. If not, then whatever you just computed still operated. Now, when we use messaging, we often want to provide an option to suppress messages, right? And the way that we can do that is often we add an argument. So here we have a quiet equals false. And this could be used. You also see verbose is another argument that's commonly used to quiet a function, like to turn the messages off. So now within my function, I just say if not quiet, right? So that would be if quiet equals true, then go ahead, check this condition. And if this condition is not met or it is met, then go ahead and return this message. and you could add more messages in here if possible. All right, so I want you to go ahead and test this out. And what I want you to do is let's go back and look at the rescale function that we created earlier. Right, so this is what it should look like. Rescale takes a vector x and then also digits equals 2 for rounding. And we compute the scaled or transformed vector that is rounded to whatever decimals we want. Now what I want you to do, see if you can do a few different things. One, move this na.rm equals true. Move that into the function arguments so that the user can control whether or not to remove missing values. And then I want you to add a warning that tells the user that NAs were present. Right? So if the user passes na.rm equals false and there's a missing value in there, then they should get some kind of a warning like what we see over here, right? That says there are, in this case, I said there are 1 NAs, remove them with na.rm equals true, right? And now we see the output is actually NA in return, right? But this is telling the user why we have NAs. It's because there was 1 NA. So see if you could add something like that. See if you could add a message that tells the user how many NAs were removed. So if they do have na.rm equals true, then what gets returned is if there is an NA in there, then it tells you how many NAs were removed, but then it still computes and it performs the operation. So what I'd like you to do is go ahead, see if you can add those, and then take the test vector that we had created earlier, add an NA at the beginning of it, right? I should still have this, and your test vector should look like this. I want you to go ahead, and after you've added this information, test your function with a few different function calls on this test vector and see what you get. They should look similar in nature to what we see here. All right, so how did I approach this? Well, so let me actually, I'm going to take this code here and I'm going to copy, well, let's see. I'm going to copy this over into my R script here so it's easier to see. All right, so let's walk through this. Okay, so I've got my rescale function here, and what I have done is I have x is my input, and now I've got 3 different arguments that are set with defaults. We have the digits, which was in the previous function that we saw, so that's not new. But we also have na.rm equals true and quiet equals false. All right, so let's see how we're using this. Well, first thing we want to do is we want to check to see if our vector is actually a numeric vector, right? And so in this case, what I am checking here is this says if x is atomic or is not atomic. So is atomic is a way to see if it's an atomic vector, right? Which is the normal kind of vector that we have been talking about in this class. All right, first of all, if x is not a vector or x is not numeric, right? We want to throw a warning and we stop and it says x must be a numeric atomic vector. All right, so we've added our warning to basically validate and communicate if x is not a numeric vector. Okay, now what am I going to do? Well, here's a line here. I compute how many missing values are supplied in x. Okay, and so then the next steps are I'm going to check, first of all, if the user says do not do not remove missing values. So if they were to call na.rm equals false, that will trigger this if statement to be true. And then what I do is I say warning, and I'm going to paste together this statement here, which is basically going to say there are, however missing n, whatever the missing number of missing values I computed right here, NAs. Remove with NA.rm equals true. So this is what computes or provides the warning if NA.rm equals false, but NAs are present. And then what I do is I'm going to add a message. So here's a message to report how many NAs were removed. So now if NA.rm equals true, which is the default, then what we do is we take X and we look for all the elements in X that are not missing. And then what I do is I say, if it's not quiet, so as long as they're not trying to make the function be quiet and not communicate back to them, then I want to provide a message that just says, however missing numbers, however missing elements, which I can put it up here. So it'll paste that back with NAs were removed. Okay? So now, I mean, here is the original source code we had for this function. And here's all the stuff we added just to communicate back to the user. Now, if we applied this function to a non-numeric vector, which letters, right? Recall letters is a built-in vector in R that's just character strings. Right, if we pass that, we'll see error, X must be a numeric vector. Now, if I take my test vector and I pass that, but I call na.rm equals false, because there is an NA in there, right? Recall, test, vector, there's an NA in there, right? Our computation is going to actually fail. And that's because when we compute the range of any kind of a, watch, if we do range of our test vector, because we have missing values, we get NA in return. Okay, so we can't actually do our computation. So we get NAs in return for each element of our test vector, but we at least provide a warning that says there are 1 NAs. Remove them with na.rm equals true. So then the user could go ahead and have na.rm equals true, which is what we do here, but the default is set to true, so they don't even need to specify that. And it will compute all the elements of our vector in a scaled format, but it also supplies this message of 1 NAs were removed. All right, so these are just examples of ways that we can combine error messages with warnings, with messages, so that we have more informative information to provide the end user of our functions. All right, so you've learned the basics of creating functions. Now let's talk about how do we distribute functions, or how do we share functions and reuse functions. Well, there's 2 main ways to do this. One is through a function called source. So say we have a script where we write functions and we save functions into. So take a look down here. I've got my functions. Let me open this up. So here's some custom stat functions, right? So I have just created some functions that compute the variance, standard deviation, the standard error, and the skewness, okay? Now, I saved all these functions in this one R script, and the idea is that when I want to use these functions, I just source this R script, and that will bring these functions into my environment, okay? So, for example, we can see that I've got this path down here, and this is the path to those custom stat functions, okay? So if I want to import those functions to use them in my environment, I can do that. Now here, let's go ahead, let's take a look down here in my global environment. The only thing I have down here right now is the path to my functions, right? But when I go ahead and I call source, and then I source that path, that code gets ran, and those functions are automatically imported into my environment. Right, so now we have the skewness, standard deviation, standard error, and variance function. So I could apply these to any kind of, well, these are designed to work on vectors, right? So I could create them on, let's see, run. I'm going to go ahead and create a vector of 10, right? And just call this test vector. And so now I can go ahead and I can compute the variance of my test vector. And I get that. I could compute the skewness of my test vector, right? So I can reuse these functions now, okay? Now the issue with this is it's easy to get started doing this. And this is something that you'll probably see done in an organization that you go work with. But it doesn't scale well, right? So in order for other people to use these functions, they'd have to be saved in a common area that anyone can source versus just having them locally. But another issue is they don't have a lot of good documentation surrounding them. There's no example usage. Basically, the ability for folks to come in and use them and understand these functions, it's more difficult. Right? So an alternative method is to actually write your own package. And we've used a lot of packages so far in this class, dplyr, tidyr, ggplot, and stuff like that. Now, you could also write your own functions, right? Or write your own package. So here's a package. It's called the VIPs for variable importance plots. And we look at this in later modeling lessons if you are in one of the classes of mine that gets into machine learning modeling. And so these are functions that originally we created to use on our own, but eventually we saw more use and other people want to use them, so we created a package. Now, writing a package is not easy to get started. Once you understand how to do it, it's not the most difficult thing in the world, but it definitely has a learning curve. However, it scales very well because you can write a package and then you can have that package hosted on CRAN where anyone with R can install and use that package and the functionalities provided in them. Now, we're not going to go over at all how to write a package. However, if this is of interest, then here is a great book, R Packages. And if you actually Google this book by Hadley Wickham, you're going to find a free version online that will basically get you up and running and writing your own R packages. Now, there's a lot of other things we can do with functions that we're not going to really hit on. One is if you want to add progress bars, you can. So here's an example of, don't worry about reading all the code right now, but this function includes a progress bar. So here, this allows you to import any data, and that's going to combine them. And so you could actually be importing 26 data sets, and that may take a long time. So you could have this progress bar, which we see coming across the top. And as this function works and iterates through each file and imports them, it's going to provide you with a percentage done, right? So that's a nice way to indicate to users how much time is remaining for your function to compute. You will see this ... used within functions quite a bit. We can actually use this to indicate we want to pass arguments to another function, right? So in this case, we do some stuff within this function, and then we call a plot function, which is just provided by R. And the plot function allows us to do many things. It allows us to color the points blue. It allows us to create a title of that function. It allows us to change the points and all that kind of stuff. But rather than write all these arguments on our own, like this is basically a function that just makes it easy to plot the strongest correlation between variables. Rather than pass all this information directly, it's already there and allowed to be passed into a function that our function uses. So you can just use ... to allow users to pass arguments that can be supplied into a function that your function is using. We can also use that ... to basically indicate that there are an unknown number of inputs that can go into this function. For example, we have seen the dplyr select function. And let's see, if we look at select here, you see that select allows us to select certain variables of interest, right? So we could say let me make sure I have dplyr loaded, right? And so I could say empty cars, and I want to select what, miles per gallon, right? I may want to select, let me go ahead and turn this into a tibble. All right, so that selects one column. Maybe we want to select 2 columns, cylinder. Maybe we want to select a 3rd column, which is displacement. Whoops. Oh, displacement does not exist. Let's do, then I think weight. Yep. So, right, we can add 1 up to however many arguments in the select function. Well, to make that work, we can actually use this ... right? And it follows this kind of unique syntax. And what this does is it just extracts all the inputs that a user provides, and it pulls that out to be used in one way, right? So this right here, this is not exactly how select is implemented, but this is a very simple version of showing how select uses the functionality of this ... to allow users to pass however number of column names as arguments, and then to use that information. We can also improve our functions by incorporating C++. So there is a package called RCPP that allows you to incorporate C directly into your R code or R functions, right? So this is something where if you're trying to improve the performance, computational time of functions, then this is a great option to check out. And there's a lot more. There's so much more. And if you want to kind of dig deep into how functions work and how we can use functions in more advanced ways, this Advanced R book by Hadley Wickham is definitely a book that you're going to want to jump into as this class is winding down. All right, so key things to remember here. Functions are a centralized, they allow us to centralize common tasks to a single abstract method for reusability. Naming your functions is important. We want it to be quite obvious what your function does. And when we define a function, we do it just like we define many objects, where we have the name of the object and then the assignment operator. And what we use here is a function call, and then we pass the body of the function within curly brackets. Think about arguments and how we have smart argument naming and ordering to make it easy for users to use. Maybe some of those include defaults. We can use various conditional checks within our functions that may help to trigger whether it's an error be thrown, warnings being issued, or messages that the user can see and have informative insight into what's going on, maybe what went wrong, and what they should do next. And then when you want to distribute functions, you basically have 2 primary options. You could use the source function to source a script that holds your functions, or you could start learning how to build a package. All right. First of all, I want you to make sure that you are digging into the lesson reading. There's much more information there. It goes through a lot of this information in more detail, along with providing more code examples. If you still have additional questions after that, hit up the discussion board on Canvas.